All right, so I want to start us off today with a sentence. It's like a tripwire.
Oh.
Yeah, to you and me, totally harmless.
Hmm.
But for a computer, it's a complete disaster. You ready?
Lay it on me.
Here it is. Lexicosemantic segmentation is a real pain in the neck.
Ah, yes. A classic trap.
Right, because I hear pain in the neck and my brain just instantly shortcuts. It goes straight to, okay, this is annoying. A hassle.
Of course.
But if I'm a computer and I'm programmed to take everything literally, I'm not thinking about annoyance. I'm thinking about, what, cervical vertebrae?
You're searching for physical trauma to a specific body part.
Exactly.
And that one misunderstanding creates a massive headache or, a pain in the neck for anyone building software that's supposed to understand human language.
So today, we're doing a deep dive into the computational treatment of multi-word expressions. Now, I know that title sounds incredibly dry.
It does sound a bit academic.
It sounds like a lecture we'd all sleep through.
Yeah.
But honestly, this is where language just breaks all the rules we try to teach the machines.
It's what the source material calls the gray zone.
I love that. The gray zone.
Oh.
So the mission for this deep dive is to figure out why computers, which can beat us at chess, fall apart when they see a phrase like piece of cake.
Well, it comes down to a fundamental mismatch. We process information one way. A machine does it completely differently.
How so?
A computer wants to split everything up. It sees a sentence and chops it into single words, what we call tokens. It wants to look at piece, analyze it, then look at of, analyze that, then cake.
But that's not how we work.
Not at all. Language is full of these chunks, groups of words that only have meaning when they're glued together. These are multi-word expressions, or MWEs.
Okay, let's unpack this, because it seems like we just need to teach the computer some slang. Why is teaching a computer to understand piece of cake, actually, not a piece of cake?
Because MWEs are not just slang. They are, and this is key, they are pervasive. They're inevitable. You can't build a good natural language processing system, Siri, Google Translate, whatever, without tackling them head on.
And if you don't?
If you ignore them, you don't just get a robot that sounds a bit stiff. You get those translation fails that go viral, you get irrelevant search results, you get AI that just fundamentally misses the point.
So we're going to look at what these things actually are, the detective work needed to teach a computer to find them, and yeah, why getting this wrong leads to some really embarrassing moments.
We certainly will.
Let's start with that gray zone idea. The source gives this fantastic example, a dry run.
Right, a dry run. Now, if you take that literally, it implies that there must be a run that is not wet.
Right. Which is just nonsense. I mean, no one talks about a humid run or a moist run unless they're actually, jogging in the rain.
But if I asked you, hey, was that a wet run? You'd just be confused. You'd be looking for a literal meaning isn't there.
Because you can't just swap the words out.
Exactly. This is what we call non-compositionality. In a normal sentence, you can predict the meaning of the whole thing by just adding up the meanings of the parts. Red flower. It's a flower. Its color is red. Simple.
1 + 1 = 2.
But with MWEs, the math just breaks. The meaning of the whole has almost nothing to do with the individual pieces.
So it's like 1 + 1 = 3.
I'd say it's more like 1 + 1 = apple pie. The output is in a totally different category. And to really get this, we have to clarify a key distinction from the source: the difference between a token and a lexeme.
Okay, break that down for us. Because token just sounds like something from an arcade.
In this world, a token is just a mechanical unit. It's basically whatever string of letters is between two spaces. Simple as that.
So it's just a chop.
Just a chop. But a lexeme is a unit of meaning, a block in your mental dictionary. So the word white space is one token, but it contains two lexemes,
Right.
white and space.
Got it. And MWEs are these items made of multiple lexemes that act like one single word. They have idiomaticity.
Correct. And the sheer variety is staggering. The source calls it a zoo of categories, and it is not just idioms.
Yeah, let's walk through the zoo. You've got your classic nominal compounds like ivory tower or machine translation.
Right. They look like a noun with an adjective, but they function as a single concept.
Then you have verbal idioms, to do the trick, to give rise. But the one that really got me was the light verb constructions, LVCs.
Oh, LVCs are fascinating. They really expose how weird English grammar is.
So light verbs. This is something like to make a decision, right?
Exactly. Now think about the verb make in that sentence. I need to make a decision.
Okay.
What are you actually making? Are you, building something?
No, I'm not baking a decision like a cake.
Exactly. The verb make is semantically empty. It's light. The entire action, the real meaning, is all locked up inside the noun, decision.
That's wild. I never thought of that. The make is just filler.
It's a syntactic handle. It's just there to carry the tense. You need a verb to make the sentence work grammatically, so you grab a light one. For a computer, that's a nightmare. It analyzes make as a creation event and gets totally lost.
And then you've got verb particle constructions, which are probably why people give up learning English. To break up, to figure out.
The plane took off. It didn't take anything anywhere. To give up. You aren't giving anything away. The particle completely changes the verb's meaning.
Okay, so we have this whole zoo of weird phrases. Why are they so hard for the machine? We've touched on the meaning part, but the source has this thing called the red herring test.
This gets at limited variability. If I talk about a red flower, I can also say pink flower or crimson flower. I can swap the adjective.
But I can't say that clue was a real pink herring.
No, you absolutely cannot. The meaning just evaporates. That's lexical idiomaticity. You can't just substitute synonyms.
It's like a password. You have to get it exactly right.
Precisely. And then there's morphological weirdness. Take to go bananas.
He went banana.
Now try it in the singular. He went banana.
He went banana. No, that sounds like he literally transformed into a piece of fruit.
Exactly. It's fixed in the plural. Or look at a phrase like by and large. That's syntactically just weird. You'd never say by in short. It violates standard grammar, but we all accept it.
Which brings us to the translation trap. The source gives this great French example. Coûter les yeux de la tête.
Which, if you translate it word for word, means to cost the eyes from the head.
Yikes, that's graphic.
But the correct translation, the MWE, that means the same thing in English, is to cost an arm and a leg.
So we trade eyes for limbs across the channel.
Cultural differences. But imagine a machine translator getting that wrong. The English speaker is going to be very confused about why they're paying with eyeballs.
This isn't just a funny anecdote, though. The source mentions that Chinese park sign.
Oh, the fire on everyone sign.
Yes.
It was supposed to mean forest fire protection is everyone's responsibility, but the algorithm didn't see the MWE. It just saw fire as a command verb and everyone as the target.
So a safety warning becomes a threat.
A very serious one.
That is high stakes. Okay, so we know what they are. We know they're dangerous if misunderstood. Now, for the detective work, type-based discovery.
Right. This is the big question. How do we teach a computer to find new MWEs in a huge pile of text without a person pointing them all out?
My first instinct is just count them. You know, if peace and of and cake show up together a million times, surely that's a clue.
You would think so, but simple frequency is a liar.
How so?
Well, what's probably the most frequent two-word pair in English?
Of the, in the.
Exactly. Of the is everywhere. But it's not an MWE. It's just grammatical scaffolding. If you only count frequency, your list will just be boring prepositions, so you need better math. You need association scores.
Okay, the source mentioned point-wise mutual information, chi-square tests. My eyes glazed over a little. What's the logic here?
Think of it like a seating chart at 1,000 weddings.
A wedding. Okay, I'm with you.
If you see Alice and Bob sitting together once, maybe it's random. But what if, over 1,000 weddings, Alice and Bob are always sitting next to each other, no matter what?
Then that's not an accident. That's a relationship.
Exactly. The algorithm compares the observed frequency, how often they are together, to the expected frequency, how often they should be together just by random chance. If the observed is way, way higher, the computer flags it and says, the odds of strong and T hanging out this much are basically zero. This must be an MWE.
I love that. It's calculating the statistical romance between words.
That's a perfect way to put it, but sometimes that's not enough. So we have method 2, the substitution test.
This is where the computer plays synonym games with itself.
Kind of. It takes a phrase like strong T, and then it generates fake versions. It searches the entire internet for powerful T or muscular T.
Muscular T. I'd try it.
If the computer finds 0 results for muscular T, that's a data point. But then it tries strong man, and it can swap in powerful man and get millions of hits.
So because the synonym works for man, but not for T, it knows strong T is special. It's rigid.
It's a measure of how resistant the phrase is to change. If the synonyms fail, the phrase prevails.
And then we get to the really sci-fi stuff, using vectors.
This is the most modern approach. We represent words as points in a huge multidimensional space based on their meaning.
Hang on, I'm stuck on the vector part. How does the computer know where to put a word like honeymoon in this space if it doesn't know what it means yet?
It looks at the neighbors. It doesn't know what a honeymoon is, but it sees that the word honeymoon always appears in sentences with hotel, flight, beach, relax.
Okay, it's social circle.
Exactly. Now look at the component parts. Honey and moon. Honey hangs out with bee, hive, sweet. Moon hangs out with night, sky, stars.
So the neighborhood for honeymoon is completely different from the neighborhoods for honey or moon.
Totally different. And the algorithm just measures that distance. It says, wow, the vector for the whole phrase is miles away from the vectors of its parts. That mathematical distance is the proof of non-compositionality.
That's so cool. And the last method is almost like cheating, multilingual discovery.
Right, you use parallel texts, the same text translated into two languages.
Like the kick the bucket example.
Yes. You have an English sentence, he kicked the bucket. And the Portuguese translation is simply, ele morreu. He died.
So 3 words in English line up with just 1 word in Portuguese.
That alignment asymmetry, that 3-to-1 mapping, is a massive clue. It basically screams at the algorithm, hey, these 3 English words are acting as a single unit.
So we found them, we have our list, but now comes the hard part, spotting them in the wild, because context is everything.
This is token-based identification, and it's where the real challenge is.
Let's use piece of cake. Sentence A, the exam was a piece of cake.
Idiom.
Sentence B, I ate a piece of cake.
Literal. And the computer has to tell the difference instantly.
How does it do that? The text mentioned bio-tagging. It looked like alphabet soup to me.
It's actually a pretty clever labeling system. The machine goes word by word through a sentence and assigns a tag. B for beginning in MWE, I for inside in MW, and O for outside.
Okay, so walk me through a sentence. I need to make segmentation decisions.
All right. I is O, outside. Need is O, to is O. Then we hit our light verb construction. Make gets a B for beginning the phrase. Segmentation. That's an adjective stuck in the middle, so it gets an O.
An outsider.
An outsider. And then decisions gets an I because it's inside the MWE, make decisions.
Wait a minute, that gap seems like a huge problem.
Yeah.
You have segmentation sitting right in the middle of your MWE.
That is probably the single hardest problem in this whole field. Gaps and discontinuities. MWEs are not always polite enough to stand next to each other.
The source had that crazy example. He took a significant number of incrementally large steps.
Exactly. The MWE is took steps, but they're separated by 7 other words.
That's a ton of noise.
And computers really struggle with that. Most systems work by looking at a word's immediate neighbors. Linking took all the way over to stacks requires a really deep understanding of the sentence's syntax. It's like trying to spot a friend across a crowded room.
Easy if they're next to you, almost impossible if they're on the other side of the dance floor.
And if you miss them, we're back to fire on everyone.
So let's wrap this up with this so what. We've dug into the tech, but how does this actually impact us?
Well, machine translation is the killer app, and the main solution is something called retokenization.
Which is what?
It's basically putting a digital wrapper around the MWA. Before the translator even starts, it scans the text, finds piece of cake, and smashes it together into one giant token, piece of cake.
So it forces the computer to treat it as one single vocabulary word.
Precisely. Then, instead of translating the parts, it looks up piece of cake in its dictionary and finds the concept easy. It prevents the literal mistake from ever happening.
That makes perfect sense. And it's huge for search or information retrieval, too.
Huge. It's all about disambiguation. The source says the word voice has 11 different senses.
And mail has 5, like Jane Mail, post.
So if you search for those 2 words separately, the computer is looking at 55 possible meaning combinations. It's a mess. But the MWE voicemail has exactly one meaning.
Identifying it cuts through all that noise instantly. A shortcut to the right meaning.
And finally, it even helps humans. Lexicography. People who write dictionaries use these tools like word sketches to find common patterns. The data tells them, hey, people don't say strong rain, they say heavy rain. Put that in the dictionary.
It really feels like we've gone from pain in the neck being a joke to realizing these phrases are the skeleton key to how we actually think and speak.
They are. We started out by calling MWEs the exceptions to the rules of grammar. But they are so frequent, you could almost argue they are the rule.
So what does this all mean for the future of AI? Where does this leave us?
Well, the source leaves us with a really provocative thought. It says we've only touched the tip of the iceberg.
Really? After all this vector math and statistical romance and wedding seating charts?
Yes, because distinguishing a dry run from a wet run is one thing. That's a math problem you can solve. But truly understanding the culture that's embedded in the language, That's another thing entirely.
What do you mean?
Why do we say kick the bucket? Why spill the beans?
Why do we say cost an arm and leg while the French say cost the eyes from the head?
Exactly. We are getting very, very good at teaching computers the math of language, the statistical likelihood of words hanging out together. But we are still a very long way from teaching them the history, the metaphors, and the culture that created those phrases in the first place. We're building better calculators, but maybe not poets just yet.
That is a fascinating place to leave it.
Yeah.
Next time you're in a conversation, just try to listen for the MWEs. Once you start spotting them, you realize you're basically speaking in code half the time.
You will not be able to unhear them.
Bear in mind, at the end of the day, for the time being.
Deep dive.
Exactly. Thanks for listening, everyone.